So now that we know a little bit more about dimension reduction and the differences between PCA and EFA, we can focus on the first of these techniques, the PCA, principal component analysis. Here the goal is to examine the correlation matrix, the total variance in that matrix, and see whether the lower order dimensions may come together to form larger, higher order components. First, it is important to remember what PCA is. PCA is a method for reducing your data into fewest principal components to simultaneously maximize the amount of variance explained. So what you're going to be doing is examining all variation in correlation matrix, and you will be assuming that there is no measurement error. So what does this mean? It basically means that PCA takes into consideration the variation in the correlation matrix, so the total variance that you have in your data, assuming that the variables are measured without any type of error. So for example, if you think about the variables that are not measured with error, the typical one example would be, say, the weight or the height of an individual. The variables that are tend to be measured with error could be something like customer satisfaction, because it involves some sort of biases that different individuals might have. Thus, PCA is truly an exploratory technique, although you can sometimes apply the techniques when you have some relevant hypotheses. But it is always important to remember that PCA often works with full information. So just to remember that you will be making an assumption of no error in measurements when you consider PCA as your main analysis. So the main goal of the PCA is to yield the smallest set of components. Some examples include examination of facial features, as I have mentioned in my previous lecture, and you might examine the facial features to identify the most important parts of the face. As I was saying, the upper versus lower part of the face. Another example might be to take a look at the face in a little bit of different context. And PCA might identify that the outer part of the face represents one component, and this component might include the jaw, the chin, the forehead, and so on and so forth, versus the inner parts of the face, such as nose, mouth, and eyes. Another example may include all dimensions that describe a product that you're trying to sell. So, for example, its shape, its size, its color, its the font size on the label, and so on and so forth. You might partition all of this information into, say, geometry and aesthetics components that would describe your products quite well. Although both of these examples are rather hypothetical, both of them represent the units for which you will have full information. So when it comes to doing PCA, how would you do it? First, as the PCA examines the correlation matrix, you need to understand what correlation is, and I'm assuming that everyone who is taking this class already has some exposure to correlations and correlation coefficients. First, we all know that correlation captures covariation between two vectors or two dimensions in this particular case. In other words, correlations will capture how similar different dimensions are to each other versus how different they might be from each other. Next, you will create a correlation matrix from the data and essentially examine whether some of the lower order dimensions tend to be more similar to each other or similar to each other enough to actually generate a new vector, the eigenvector, or the new dimension that subsumes the lower order dimensions. The eigenvector naturally would be quite useless if we do not know how much variance in the matrix, the proportion of total variance, it might explain. And this information would be obtained from an eigenvalue, so that is associated with the eigenvector. In other words, PCA will look at the correlation pattern and decide whether some dimensions are closer to each other to warrant inclusions into single components, at the same time trying to explain the most variance in your matrix. Suppose that you have run your PCA, examined your correlation matrix, and you end up with a whole bunch of eigenvectors and eigenvalues. And you have all of the possible components. So how many total components can you extract? The question might seem tricky at first. However, if you think about it for just a second, you will realize that the total number of components is going to be equal exactly the number of the dimensions that you have in the beginning. However, some of these components will explain more of the total variation in the matrix than others. But there are some rules for making decisions about the number of components to actually retain, because you don't want to end up with as many dimensions as you started with. So one of the rules that people typically use is going to be the Kaiser-Gutmann rule. And here the number of components is going to be equal to the number of components with eigenvalues that are greater than 1. Number 1 in here sounds quite arbitrary, but there is actually a reason for why we're looking for components with eigenvalues greater than 1. If you think about your correlation matrix, you will have ones across the diagonals. And ones will be representing the item correlation with itself, so dimensions correlation with itself or the variance. Kaiser-Gutmann rule basically states that to have a component that is meaningful, the variance in that component should be at least that of the standardized single dimension. So 1 within your diagonal. Fairly straightforward. Another way, which is quite frankly very similar to the Kaiser-Gutmann rule, would be to take a look at the total variance in the matrix that is explained. If the total variance in the matrix is 1, you can examine how much of the variance is explained by each component in terms of proportion of 1. So once you go from one component to another, you will be looking at the cumulative variance that's one component plus two components explained within your matrix. A good solution will typically explain at least 50% of variance, but most researchers, most people, and most data scientists would go for about 75–90% of variance explained. This is quite reasonable, however, the cutoff point is quite arbitrary. Think about how much variance you're trying to explain in your data and go from there. Finally, there's a third method, and it is called the scree plot method. And the scree plot basically graphs each component and the variance that it explains, and it is looking for the point in the plot where the addition of a new component is not going to explain any additional variance in the correlation matrix. So once you see that, you stop extracting the factors. Finally, there are other types of analyses that you might use, such as a parallel analysis, which is less popular, however, is supposed to be the most accurate. And we will cover this analysis in more detail in the once we actually start running the PCA.